grade 11s, welcome to your physical sciences show on a Tuesday. I am Luni and with me in studio is TK. Hi TK.
Yes, I'm good. How are you, Luni?
I'm good, thank you. What are we doing for the grade 11s today?
We are here for electrostatics, and that's a grade 11 lesson, but it's a section that actually cuts across, so everybody's going to benefit, but for now, it's mainly focused on grade 11.
All right, Mindsetters, I hope you're excited for the show. Remember to hit us up on Facebook, on facebook.com/LearnExtra, and then on Twitter, our handle is @LearnExtra. And if you want to win yourself this awesome Casio calculator, all you need to do is complete the Test Yourself section from our notes, but the link is on our Facebook page. And remember, guys, if you want all the show notes, all the videos, and all the schedules to help you revise and get prepared for your exams, all you need to do is go to learn.mindset.co.za and get all your stuff there. Remember, Casio calculator, the competition closes next week, Tuesday, so you have all the time in the world until 8 a.m. in the morning on Tuesday next week to enter this competition. So watch the show now, have fun, take down notes, and be prepared for your exams and all of that stuff. And TK is going to give us a great lesson.
Yes, thank you, Luni. Let's start now. We're talking electrostatics. And what is this? Electrostatics has to do with charges, so we'll be talking charges here, okay? And of course, we're talking what we call stationary charges, okay? So let's move on here. In this lesson, of course, we'll be looking at objects. We will identify and see how objects end up getting charged. That's what we're trying to say is here is how do we get objects to finally or at some point get to have a positive charge or a negative charge. Okay, and we're going to review what we call the law of conservation of charge. We are also going to state and apply Coulomb's law. And we're also going to describe what is meant by electric fields and show how to calculate the electric field strength, of course, at specific points around charges or, of course, between charges. Okay, now moving on, we're going to have a challenge question as usual, and here it is. Take it down. Okay, the electric field strength, okay, at a point A, which is x meters from the charge Q, is E. It's E. And of course, we know that electric field strength is measured in newtons per coulomb. It is E newtons per coulomb away from charge Q. Without changing the size of the charge Q, how can you reduce the electric field strength at that point, which is point A, to 0.25 E newtons per coulomb away from Q? Okay, so we're going to look at that. Let's quickly go through this summary here. What is a charge? Or let's look at what this thing called a charge is all about. In electrostatics, of course, we're talking about stationary charges. We're talking about those charges that are not moving. So we're not talking about electric current. We're talking about those that are stationary. Okay? And these charges, of course, are found on the surfaces of insulators. The charge is symbolized by a letter Q, and it is measured in coulombs. And of course, after the scientist Coulomb, who came up with the Coulomb's law. And the SI unit for this, of course, it is the C, the coulomb. All right. Now, moving on. The coulomb, it's a very, very big unit. So we usually use very small units. We therefore use units that are smaller to handle, easy to work with. Units like microcoulombs, nanocoulombs, microcoulombs, and what we call picocoulombs. Now, what is necessary here is that you need to be able to convert from the unit in which the charge is going to be expressed to you to the required SI unit. Remember, when we do your calculations, we expect you to use the SI unit. Okay. Now, you need to be able to convert from nanocoulomb, from millicoulomb, from microcoulombs, from picocoulombs to coulombs. All right. An object becomes charged when it gains or loses electrons. Okay? So what actually happens here is that it's only electrons that move around. Remember that objects are made of atoms. Atoms have got nucleus, where the positive charges are found, cold protons, and the neutrons that are neutral. These ones are not moving. But around it, in energy shells, we've got what we call electrons. So when these electrons are gained by another object, that object becomes negatively charged. When these electrons are lost by an object, that object becomes positively charged. So the charging of objects are actually as a result of the transfer of electrons, either gained or lost by object. If an object loses electrons, we know, or I've just mentioned now, it will become positively charged, because at that point it has got excess positive charges compared to negative charges. If it gains electrons, of course it will have an excess of negatively charged particles. It will therefore become negatively charged. Okay, now the charge on an electron is 1.6 by 10 to the power minus 19 coulombs. Okay, right, now moving on with the summary, coming to the law of conservation of charge. We know that charge can neither be created nor lost. Okay, so it is there. This whole universe has got a particular number, a strict, okay, a particular number that is not, it can never be more, it can never be less. So if objects get charged, it's actually the charge that is there. It's either the gain of electrons or loss of electrons that are there. You can never create charge, you can never lose it. The total amount of charge in a closed system remains constant. Now our closed system here is the whole universe. Okay, it remains constant. There are an equal number of positive and negative charges present in the universe. Okay, when charged objects touch, okay, when they touch each other, charge will be distributed, and this is very important, evenly and equally on the surface of both objects. Okay, and this equation here helps us to know how to find the new charge on objects when they come to touch each other. If I've got two objects, they come to touch each other, the new charge will be found by adding the charge on 1 and the charge on 2 and dividing by 2. What does it mean? Would I always have two objects coming to touch each other? I can have more than one, but if you have more than one, what does it mean? Say I've got 3. It means you would say Q1 plus Q2 plus Q3, and you'll be dividing here by 3. Okay, so that's what it means. So understand this formula here, which is very, very important. And of course, it is applied when we consider the fact that charge is conserved. Charge can neither be created nor destroyed. It can only be transferred from one object to another. Okay, the next on our summary, let's talk about the force between charges. Okay, if we have charges, we will have a force existing between them. If I've got like charges, say positive and a positive charge, because they are like charges, they are going to have a force of repulsion between them. Okay, so they will repel each other. And on the other hand, if I've got unlike charges, a positive and a negative, the force that will exist between them, it's an attractive force. It's a force of attraction. They will attract each other because they are carrying opposite charges, positive and negative. All right. Now, the force between charges is described by Coulomb's law. Okay? And we also need to know that force is a vector quantity. What do we mean by this? Every time you talk about force, you need to express it in both magnitude and direction because it is a vector quantity. Coulomb's law states that the electrostatic force between two charged objects is directly proportional to the product of the charges and inversely proportional to the square of the distance between them or between their centers. Okay? And mathematically, we can look at it in this way. Okay? The force equals, in fact, directly proportional to the product. So Q1 times Q2. and inversely proportional to the square of the distance between them. But now, as an equation or as a formula, we now have an equal sign, not a proportionality sign, because we have multiplied by a constant called K, which is what we call Coulomb's constant. Okay? And of course, the value of the Coulomb's constant, we're going to see it down here. F is, of course, the force, and it is measured in newtons. Q1 and Q2 are charges, and we measure them in coulombs. So if they are given to you in microcoulombs, nanocoulombs, whatever, picocoulombs, you must be able to move from those units to coulombs. Okay. R is the distance between the centers of the charges, and we measure that, of course, in meters. K is the Coulomb's constant. It is always equals to 9 by 10 to the power 9 Newton meter squared per square coulomb. All right, that's what it is there. Next, on our summary, let's have a look at the electric field patterns. If I've got a charge, this time here I've got a negative charge here. The electric field will be shown as lines around that charged sphere. And because it's a negative charge, the direction of the field will be inward. It will be going into the object. Why? Because the direction of the charge, of the electric field, is determined by putting a test charge, a small point positive test charge. The direction that it will take gives us the direction of the field. So if this charge is negative and this, as we know it, the test charge is always positive there, it will move towards the object that is negatively charged, and that gives us the direction. If this sphere was a positive sphere, okay, this positive charge or the test charge was going to be repelled, going away from the object. And in that way, it means we will then change the direction of the field there in that way, okay, if that was a positive, okay, that's what it means. Now, if I have two oppositely charged spheres, like I have here on my right, you would see that if they are in the field of each other, because they are positive and negative, they're showing a force of attraction. They're actually showing a field that says there is attraction between them. They attract each other, okay? And that field, of course, would not behave differently to the electrostatic force that would exist between them. And because electric field as well, it's a vector quantity, we also need to show the direction in which this field is moving. So hence we have the arrows to show the direction here from positive to negative in that way. If I've got like charges result in a repulsion, force of repulsion that exists between them. So even the electric field around them will be repulsive in nature. So you would see that with positive and positive, this is what I would have. In the same way, even if I had negative to negative, the only thing that would be different here, if it was negative to negative, it would be that the direction was going to change. So I would have used an arrow that points inwards into the object to show that the electric field comes into the object that is negatively charged. Okay, and that's all. Right, now, moving on, let's talk to the electric field strength. Now, electric field strength, we use the letter E, capital letter E, to show the field strength. The field strength at a point is the force experienced per unit charge at that point in the field. Electric field, therefore, the electric field strength is a vector quantity, like I've already mentioned, and therefore we need to treat it as a quantity that must be expressed in both magnitude and direction. Okay. Now, we are saying electric field is force per unit charge. So it suffices that that should be the equation or the formula in which we are to calculate for it. Where E is your electric field strength, it will be in newtons per coulomb. You can see from here, force is measured in newtons, charge is measured in coulombs. Obviously, this leads you to newtons per coulomb, and that is where that unit comes from. So force, we know it. It is measured in newtons, and Q measured in coulombs. Okay. When we're talking electric field, okay, this can also be expressed by, because we can actually look at what is the strength of the field at a point away from a charge. And when we look at it in that way, we use this formula here that says E equals KQ over R squared, where R is the distance of that point away from the charge where we want to know the strength of the field. Okay, so E equals the electric field strength, of course, and Q is the charge. But what we didn't have is R, the distance from the charge, which is in meters, and of course K again, which is the Coulomb's law, and it is of the value 9 by 10 to the power 9 Newton meter squared per coulomb. All right. So that is the theory or the background information that you need to have to be able to deal with problems based on electrostatics, starting from charges. Okay, positive and negative charges. These charges are stationary. We're talking about electrostatics. Okay, electric charge. Statics, from the word stationary. So we're talking about charges that are not moving and looking at how they would behave. Okay, and from there you look at the fact that between charges we would have a force. We call it an electrostatic force, and Coulomb says that force will be given by F equals K Q1 Q2 over R squared. Okay, from there we're talking about the field due to a charge. Okay, field due to a charge, E equals F over Q, because we define E, the electric field strength, as the force experienced per unit charge. Okay, and we measure that, of course, in newtons per coulomb. All right, and from there, another thing that I'm trying to give you a quick summary on that is the fact that you need to look at the conservation of charge, the law of conservation of charge, where if objects that are charged come together, the charge will be distributed equally or evenly, and then you can actually find a new charge on each sphere thereafter. So that actually is the summary that we had. Let me just hand back to Luni now and see what I think in the meantime you will be preparing your questions and also looking at your challenge question. But let me hand back to Luni and we'll see what to do from there.
Okay. Mindset is, as you've been hearing throughout the week, we have SA National Games, water games that are going on. So all you need to do to enter this competition, all that happens is that it's to see what you think of the South African water issues. So all you need to do is go to www.watergame.co.za, register yourself, and then you start playing, and you can stand a chance to win awesome prizes, guys. Remember, more information about the game is on our Facebook page, so you can go to facebook.com/learnextra, get more information and register yourself. Remember, if you see a blank page whilst you're registering, don't worry, guys, just wait a bit and then it will take you through to the page and you can start playing the game. But now let's take a very quick break and we'll see you straight after this. Welcome back from that break, guys. I hope you're still enjoying the show. I'm not going to waste any more of your time. I'll take it straight back to TK. Thank
you, Luni. Let's move on, and we've got a couple of questions that we have to work on, and of course, very, very good questions. So you sit down and you learn with me. Let's just go through them now. We're looking at question number 1 now, trying to improve our skills on how to answer questions, exam questions, of course. It says here 2 isolated charged spheres, A and B, are suspended from thin strings and brought closer or close to each other. The charges experience a force of attraction. So if it's an attraction, so it means one charge is positive, the other one is negative. They touch each other and then move apart. The original charge on A was plus 5 microcoulombs. And the charge after touching is minus 5 microcoulombs. The first question says, calculate the original charge on B, on sphere B. All right, now let's have a look at it. We know that Q nu, we have got two spheres, so we would say Q nu would be equal to Q on the first one plus Q on the second one. And because they are 2, we divide by 2. All right? Now, the new charge, and of course here I don't have to convert here because I'm just interested in the new charge, but I can convert later on to work out other things. But then let me just work it out because we will be expected to convert, so let's use the opportunity to learn to do that. Now, if the new charge, okay, the original charge on A was 5 and the charge after touching is minus 5 microcoulombs, it means the new charge is minus 5 multiplied by 10 to the power minus 6. That's the new charge. So let me change here and call them QA and QB because the question is very specific. It refers to them as charge on A and charge on B. Now, other information that I have from the question is that the original charge on A was plus 5 microcoulombs. Okay? So 5 microcoulombs, it's 5 by 10 to the power minus 6. Then multiplied by the charge on B. That is what we are looking for, divided by 2. Okay? Now, if I am to work this out, this is going to be obviously minus 2 by 10 to the power minus 6 equals positive 5. Let me put the positive 5 there, by 10 to the power minus 6 plus, that cannot be a multiplication sign, plus QB. All right. Therefore, my QB would be equal to, okay, so this 2 times that should be minus 10. 2 times minus 5 is minus 10 by 10 to the power minus 6. Now, if I'm looking for QB, I need to take this one to the other side. And what is it going to be? It's going to become minus 5 by 10 to the power minus 6. Minus 10 to the power minus 6 minus 5 by 10 to the power minus 6 will give me minus 15 by 10 to the power minus 6 coulombs. So that was the original charge on B. Okay, sphere B was minus 15 by 10 to the power minus 6 coulombs. Okay. Now let's look at the second one, and of course it's a build-up from the first one. It says how many electrons were transferred when the spheres touched. Indicate the direction of transfer as well. Okay. Now look, you had QA coming into contact with QB. Now we've just calculated that QB had a charge of minus 15 by 10 to the power minus 6. Now, when an object gets charged, the reason objects get charged is because objects would transfer electrons between each other or amongst each other. Now, only those that have got excess electrons will be able to transfer. QB here has got a negative charge. Definitely it's the one with excess electrons, and therefore electrons will actually be transferred from B to A. So that will be your electron transfer. It will be from B to A, electron transfer. Okay, now calculating how many electrons have been transferred, we will need to check if this was the original charge on B, and finally the charge on each of the two spheres is minus 5 by 10 to the power minus 6. How much has been transferred from there? In fact, look at that. Okay. This, after B it comes to contact with C, with A, what we see happening is that we have about minus 10 by 10, minus 10 by 10 to the power 6 coulombs of charge there. Now, how many electrons are there? Let's look at the difference here. The difference between the original charge and this charge here, it's going to be minus 10 by 10 to the power minus 6 coulombs. And if we want to know the number of electrons will be equal to the charge that has been, amount of charge that has been transferred. Okay, amount of charge that has been transferred. And the amount of charge that has been transferred, we found it to be 10. So we'll say that we will divide this by the charge on an electron. Charge on an electron, it's minus 1.6 by 10 to the power minus 19. Okay? And that should give us the number of electrons. Now, number of electrons, how do we get that? For that situation there, you definitely need your calculator to get that. Okay? So you will say that the number of electrons that have been transferred, okay, it will be minus 10, okay, because it's minus and minus, just allow me to just say 10, 10 to the, by 10 to the power minus 6 divided by 1.6 by 10 to the power minus 19. Okay, hope I got everything okay there. Then you get the answer there. So how many electrons have been transferred? It's 6.25 by 10 to the power 13. 6.25 by 10 to the power 13 electrons. That's the number of electrons that were transferred. Okay, good. Now, moving on. Question 2, okay? Consider the diagram below, not drawn to scale, all right? And 2.1 says, draw a free body diagram for all the electrostatic forces that act on Q1. Now, there is our Q1. Electrostatic forces only that are acting on Q1, not any other force. And therefore, we are going to show only two forces here because the electrostatic forces on Q1, it's a force due to Q3 and it's also a force due to Q2. And that would mean I would have my dot to represent the what? The sphere. Remember how to do force diagrams, free body diagrams. You use a dot to represent that object. And then we know there's a force of attraction here between Q1 and Q3. So this will be the force due on Q1 due to Q3. Okay? And of course, if you look, that is minus 6, this is minus 5. So this one should perhaps, in fact, should be longer in length compared to the other one because it has got a bigger charge there. So this is a force on Q1 due to Q2. Okay? You do that, you have answered that question there. The next one is, okay, so that is where perhaps we could have done that. Let me just do that quickly. That's F due to Q3, and that is F due to Q2. These are forces, all forces on one. Let me be consistent here, all forces on one. I can put it like that. Nothing wrong about it. Okay, moving to the next question on this one. It says, calculate the magnitude of the electrostatic force between Q1 and Q2. Now, electrostatic force F is found by K times Q1 times Q2, okay, divided by the square of the distance between them. So that will be equal to, K is 9 by 10 to the power 9. It's a constant, times you look at what is Q1. Q1, it's 4 microcoulombs. So I need to convert that. So it will be positive 4 by 10 to the power minus 6 times Q2. Q2 is here. It's minus 6 microcoulombs. So that will be times minus 6 by 10 to the power minus 6, converting into coulombs. And then dividing by r squared, okay? R squared. Now, what is this? Here, let me put it down here. There was something missed on this question. That's 15 meters, and let me also put this one here. This one is 100 millimeters. Okay. Right now, and due to this length here, let me see if that is 15 centimeters. Definitely, this should be. Let me make it 100 meters. Okay. Now, so what is our R there? It's 15 centimeters. We don't work in centimeters. And this, let me just go back here. That should be 100 centimeters. So at least we have got units that are relevant here. 15 meters there, 100 centimeters there. Let's come down here. It's 15 centimeters. I can't work in centimeters. I have to work in meters, so I convert that. You divide that by 100. So this will be 0.15 squared. And that is equal to, at this point, you bring your calculator because you have to find a solution to that problem there. Okay? So let me see if I can put it that side, and we have everything to view here. So you've got 9 by 10 to the power 9 times 4 by 10 to the power minus 6 times minus 6 by 10 to the power minus 6. All right? You close those brackets and you divide that by what? 0.15. 0.15, but that must be squared. Okay, and what do we get? So what we get there, it's a force that is minus 9.6. So minus 9.6 newtons. And what does this mean? It means you've got 9.6 newtons and the force is attraction. It means you've got a positive and a negative charge that are closer to each other there. Next, let's look at the next question here. It says, calculate the net electrostatic force. Now, this is a good one on Q1. How do we do that? Now that we have got a force due to Q2 on 1, let's see what the force due to Q3 on 1 is going to be. All right, let me work it out here. That will be equal to K, Q1, and Q3, this time divided by the R squared. And that will be equal to K, we know is 9 by 10 to the 9, times Q1 is positive 4 by 10 to the power minus 6, and Q3 is minus 5 by 10 to the power minus 6. You divide all that by what? By 100 centimeters, you convert that into meters. You divide by 100 there, it's going to be 1 meter. 1 meter must be squared, okay? And you work that out. Let's use our calculator quickly, all right? You just straight away use that. So this is 9 by 10 to the 9 times 4 by 10 to the minus 6 times what is this one here? Minus 5. So minus 5 by 10 to the minus 6. Okay? We're dividing by 1. Okay? Anyway, it's just formalities. We know that 1 would remain, won't change anything there. So what do we have there? We have got minus 0.18. Okay? So this is minus 0.18 newtons, which is 0.18 newtons attractive. okay? Okay, now if you come back here, because they need the net force here, if you come back here, this is 0.18 newtons, and the other one is what we found out up there, which is 9.6, all right? So you can say that this is 9.6 newtons. Resultant here, or the net force here, you need to say, okay, they are at right angles to each other, so you can use this. You can say F net squared on Q1 will be equal to F by Q2 squared plus F by Q3 squared, right? Using Pythagoras here. So that will be equal to 9.6 squared plus 0.18 squared. And what is that? Use our calculator quickly. All right. We have 9.6 squared plus 0.18 squared. What do we get? And that must be squared, because F net must be equal to the square root of that. Okay, so we square it, of course. That's 92.19. 92.19. That should be equal to. Okay, back to our calculator. We are to get the square. So we're getting the square on the answer. And what will that be? That will be 9.6 newtons. Okay, so that gives us 9.6 newtons. Now remember, it is a vector quantity. We need to get direction. So we need to find the angle that it makes with the horizontal. It will be tan theta, because this will be opposite and that will be adjacent. Okay, so tan theta will be equal to opposite. It's the what? Is the 0, opposite is the 9.6 divided by opposite is 0.18. I mean, adjacent is equal to 0.18. We work that out. We get the tan theta. All right, that is 9.6 divided by 0.18. And what's that? It's 0.533. Therefore, theta is equal to the tan inverse of that. I think everyone can get that. And you would say that angle, actually, it will be this force here at an angle of theta there. We are there with the answer. Let me give it back to Luni.
All right, Mindset, it's time to take a very quick break, but don't go anywhere. We'll be back with more Learn Extra Live after this. Welcome back, Mindsetters, from that break. A reminder, guys, when we take your questions right at the end of the show, if we don't get through all of them, we do have help desks in store for you guys to send all your questions through and you'll get your answers. One of them is learn.mindset.co.za/helpdesk, but I've posted all three options on our Facebook page, so go check out our Facebook page for all the help desk options and send your questions through there if we don't get through them by the end of the show. TK?
Thank you, Luni. Let's just move on. We are to look at our challenge question now, and thereafter we would try and have time to look at your questions that you sent us. Let's look at this question here. It says the electric field strength, so E, at a point A, which is x meters from the charge, is E n per coulomb there. Now, without changing the size of the charge Q, how can you reduce the electric field strength at point A to 0.25 newtons per coulomb away from Q? Now, we know that here E, in this case, because we're looking at a point somewhere away from the charge, we're going to use that equation there. Okay, we're going to use that equation there. So we've got a point X somewhere there, and we have got a charge somewhere here, all right? And remember, there's a distance between the charge and the point X, and that is our R there. We want to make E to be equal to 0.25. So E nu must be equal to 0.25 E. Okay? Now, that is the new one. If we don't do anything with Q, what are we going to do to make sure that the electric field strength is brought down to that point? We can then bring another charge, okay, to some point V and make sure that the distance of our charge Q from the point X is the same distance of the charge or the point X from the original charge here, which is this one here. If we do that, it means that we need to play around with that charge because we don't want to change this one. This one must not be changed, not to be changed. So we can put something there that will bring the electric field strength here less. Why? Because the resultant E net here will be due to the two charges, this charge and that charge, and obviously it would be lesser. Okay, now what will that charge be? We started with, if you like, 1 E, and we wanted to make it 0.25 E. And we haven't changed anything else. We didn't change that. That is a constant, of course. And this, we have just doubled it, okay, from there. All right, now this charge here must be in such a way such that the E here can be brought down to 0.25. Remember, X is the same. The distance R, let me just put R. R is the same. So this charge here must be equal to, it must have 0.75 E to be able to bring us 0.25. How do we do that? E nu should still be equal to K Q over R squared. But R is the same. So E nu is 0.25. That should be equal to this KQ over R squared is 1, okay? Which is that of due to the first charge there. All right. So 0.25 there, and one of the, I mean, if that is 1, it's 1 of the KQ of the second one divided by R squared, and R are the same. So we can say that, and remember Q is the same. So it must be such that this 0.25 there would be equal to 1 KQ over K2 over R squared, R2 squared. If you work it out there, you should be able to say that this 0.25 E should of the second charge, I mean of the new electric field should make our charge here to be 0.5. Sorry about this one here. 0.5 what? 0.5 C here, which is coulombs there. All right. So that is how you would look at it. All you need to do is bring a charge here that will bring down the electric field there. So that should be 0.75. 0.75 coulombs to bring that one down to 0.25. Remember, it was 1 first. So if you take 0.75, you will bring it to 0.25. That's 1 minus 0.75, giving us 0.25. So that's what you should have done there. Now let's come to some of the questions that you have, and let's see if we can be able to answer most of them. I know that we always don't have much time to deal with them, but let's see how many we can look at.
All right, I've been reading through the questions, and most of the mindsetters have a problem with question 1. So if you could go through that.
So back to question
Yes.
1. Okay. Question 1. There we go. Yes, question 1.
Errol was asking you to do the whole of question 1 because he didn't understand.
Oh, okay. Let me just then flag it for him. There it is. It's Errol.
Yes.
Errol, we are given what Q nu is going to be. It is minus 5 by 10 to the power minus 6. This is given in the equation. But Q nu would be equal to the charge on A plus charge on B divided by 2. Okay? So we would say, because we want to know what is the charge on B, what was the original charge on B, we will put in what the new charge is, which is minus 5 by 10 to the power minus 6, equals the charge on A, which is given to us. The original charge on A is given to us. It's positive 5 by 10 to the power minus 6. Okay, plus charge on B dividing by 2. When you do that, you will find the charge on B to be minus 15 by 10 to the power minus 6. This is the original charge on B. Now, original charge before they came into contact, before they came to touch each other. Now, I also know that in the questions, we also have those that are saying, why this formula? Okay, we're saying the Q nu will be QA plus QB divided by 2 because we're looking at 2 spheres. If I had 3 spheres that came together, I would say QA plus QB plus QC, and I will now divide by 3 because the charge must be distributed evenly amongst all of them. If I had 4, the same thing, I would divide by 4. If I had 10, I was going to divide by 10. But usually we limit it to 2 for you. But don't expect a situation where you can't have 3 or more, okay? You can have them. But just understand the principle that charge is distributed evenly amongst those objects.
Okay, that answered Silindo Kutle's question as
yes,
well.
no Kutle, yeah.
Yes. And then Bongi is asking, on question 2.3, how did the distance of 1 come about?
How did the distance of 1 come about?
Yes.
On question
2.3.
Okay, 2.3. Let's look at 2.3. Now, the distance of
1
come about. Now,
Yes.
let's look at it. What's the name again? Bongi.
Bongi, yes.
Okay, now look at it, Bongi. I said here I had 15 meters there. Oh, sorry about that. I had 15 meters here, and look at this one here. Here I had 15, this should have, it's actually centimeters there, all right? And here I had 100 centimeters. So if you convert from 100 centimeters to meters, you divide by 100. When you divide by 100, okay, you would find that you've got 1 meter. That's how 1 came about. Okay.
Okay. And then Peter is also asking, aren't we supposed to work with centimeters? Because on 2.2, you changed 1.5 meters into 0.15 centimeters. But then on 2.3, you changed 100 centimeters into 1 meter.
Okay. Now that was the issue. There it is, 15 centimeters. Must have made a mistake when I put in the distances there and wrote 15 meters. Actually, it's 15 centimeters. And that's why it also had to be converted. So 15 centimeters to meters should be 0.15 meters because you're going to divide this by 100. Okay? That takes you to that.
Right, no, thanks.
All right, that's it. So we've come to the end of the lesson. Yeah.
Okay. Thank you so much, TK, for the lesson. Mindsetters at home, thank you so much for tuning in. Remember, if we didn't get through all your questions, our help desks are there for you to ask all your questions. The information is on our Facebook page. Remember, if you have any problems with the SA Water Games website after you've registered, and if you get a blank page, just be patient, guys. It will work out eventually because I've seen a lot of you are having problems with that, but please be patient and you'll be able to play the game. Remember to hit us up on Facebook and on Twitter and send us all your comments and all your questions. But from us, until next time, thank you so much for tuning in. Goodbye from us.